Hi class, I just wanted to go over a couple questions from the last take-home quiz. So all of us are on board with the same ideas here. One of the questions was that you have cyclohexanone and you're treating that with ethylene glycol in presence of an acid. So of course, as you can envision that there are lone pair of electrons on oxygen, they're going to pick up that proton and you're going to see activation of that carbonyl, because now you have a protonated system. Oxygen with a positive charge is not going to be very happy. It's going to attract the electrons towards itself, leaving behind a positive charge, or I should say more positive charge, a stronger positive charge on the carbon. So it's going to start looking like an OH with a positive center at the carbon, which is where your ethylene glycol will attack, just like that. So that now you have an OH and OH with a 1, 2, and 3 positive charge. Since you have a lone pair of electrons right here, and this oxygen, having made 3 bonds, is not very happy, it's gonna quickly pick up that proton. So a proton exchange is going on there, and you're going to end up with OH2. You could have shown that, since this is all going in aqueous medium, you could have shown water picking up that to give hydronium ion, and then this OH picking that up from water. That's okay too, but I'm just showing both of those at the same step. And now water leaves behind a positive charge again, as it does. Let me... So as it leaves behind a positive charge. And that is where the oxygen will attack, the lone pair on oxygen will attack. First, it will have a positive charge because it's making 3 bonds again, and then water can come in and it can pick up that proton, take that away, so that you end up with the protected ketone. In other words, you have your acetal. So it's important to make sure that you start with a 6-membered ring, and you're basically protecting that ring using this ethylene glycol molecule. Of course, if it's a box problem, you really don't need to show me the mechanism, but I just worked through that for you just in case you had a question about it. Another question was that you have cyclohexanone, and you're treating that with a Grignard reagent, and the Grignard reagent in question was a phenyl magnesium bromide, and then you're doing a hydrolysis, so that's the second step. So that's simply the addition of the pH across the C double bond O. It's a 1,2 type of addition, and since it's a ketone, it's going to give you a tertiary alcohol. So after hydrolysis, you will end up with OH, and the new pH, the carbon ion from here, is going to get added across the C double bond O at the electrophilic center. And now I'm subjecting that to POCl3, which is a dehydration condition in presence of pyridine. And what it's going to do is going to give you the most substituted alkene. In this case, it doesn't matter whether you utilize A or B, one or the other carbon is going to be utilized in getting the double bond in your molecule. Okay, let's take a look at the third question. It was something to the tune of, we have an OH here, double bond, and then another OH. And I'm treating that with BH3 DHF, that's my first step, following with H2O2 NaOH, and the last step is PCC with CH2Cl2. PCC converts an alcohol into an aldehyde, In this case, realize we have a tertiary alcohol here, a tertiary alcohol over here. Essentially, this BH3THF is simply going to just carry out the reaction at the double bond. That's the reactive side, and it's going to have to follow the Markovnikov's, anti-Markovnikov's rule. So it's the less substituted location which is going to get the OH, and once you get the primary alcohol, it's going to give you the aldehyde from there. Realize that the tertiary alcohol on either of the sides are not going to participate in reaction, so your final product should be 2 and a double bond H, 2 carbons, and an OH. And the last question in this particular case was that you have styrene that is subjected to bromination, Br2, with water. Recall from Organic 1 that it goes through the bromonium ion, and the attack of water is going to be anti. That means you could either draw the Br pointing upwards or pointing downwards, but the incoming water is going to come from a direction that's opposite to it, and in this case it's going to ring open that benzylic position carbocation, so that you end up seeing, if let's say it was pointing upwards, this is the product that you're going to end up with. And now that you treat it with sodium hydroxide, NaOH, followed by hydrolysis, H3O, H2O, what you're going to see is essentially deprotonation of that alcohol, so you're going to see an O negative, and then that's going to attack, so it's an intramolecular Wittig that's going on, so you're going to see an epoxide pointing downwards. And now when you carry out the hydrolysis step, that is going to ring open the epoxide again in the direction such that it gives a benzylic carbocation, and so you're going to end up with an OH on top, one OH pointing at the bottom, so one at the bottom, one at the top. It is going to be a trans addition. And now when we subject that to HiO4, and that's your hint right there, that gives you benzaldehyde and formaldehyde, because it would cleave right in the middle. It's a nature of a periodic acid to cleave diols. It cleaves diols and oxidizes them. That means you're going to end up with benzaldehyde and formaldehyde from this reaction. Alright, let's take a look at another mechanistic problem. So you were given essentially these two starting materials, and in presence of an acid HCl aqueous conditions, this is the product that you're seeing. Hopefully you're able to track the two methyls, so hopefully you can see that essentially this particular reagent is going to generate this acetal, and that's the key thing here. So first thing that I would suggest that you should think about is the fact that you have lone pair on oxygen and you have pi system. Of course, between the two, the pi electrons are more mobile because they are shared between two atoms rather than oxygen lone pairs, which are essentially in an sp3 hybridized center. They belong only to oxygen, so you wouldn't want to use that up in this particular case. And when you carry out the protonation of the double bond, which is, like I said, more mobile, this is the carbocation, versus the other option is that you could add the hydrogen right here and get a secondary carbocation. Realize the presence of lone pair of electrons in this case makes this stabilized due to resonance whereas the second one, it actually has no stabilization other than the fact that it's a secondary carbocation. And so that is the reason that the first one that I wrote, that is a better structure, and that is the structure that you're going to see first, that'll get formed. So you can absolutely write down let's say a positive charge on oxygen. Of course, the second one is a minor structure because it has a positive charge on the oxygen, but nevertheless it still is possible. So what you can show then is that because of that positive nature, essentially the electrons move back and positive charge comes back to carbon. And when that happens, really realize here that you have maybe I should go ahead and number that. So carbon number 1, 2, and 3. So 1, 2, and 3. So at that point of time, you can show the attack of the lone pair on oxygen onto this carbon, which is going to give you essentially an oxygen right here, and an OH. This will have a positive charge which can be lost to water. So let's just show that. Water will pick that up. Electrons move back on oxygen. And next, let's take a look what is going to happen. Really realize that there is lone pair of electrons on this oxygen. So that will go through protonation. So let's make some room right here. You're going to see protonation of the oxygen. And then that is going to pull off the electrons from one of the sides, and it's going to be from this side for the same reason that it's next door to oxygen, which can stabilize that positive charge through a double bond formation. And in that process, you can show the attack of the lone pair on that side. So on one hand, you're going to end up with the methyl groups right there, positive charge still, 1, 2, 1, 2, 3, 1, 2, 3 OH, and then water can lose that last proton and give you your desired acetal. Realize, since this was acidic in nature, at no point of time did I show a negative charge, and you should do the same thing. You cannot show a negative charge on any of these structures because it is an acidic medium where the reaction is taking place. Okay, let's take a look at the third question. It says here, treatment of aromatic compound A. So A is some aromatic compound which is treated with an alide CH3, CH negative, PPH3. So hopefully those of you who were present in the last two classes would recognize this as the Wittig reaction, and it gives you B and C together, and it's given that these are isomeric in nature. So these must be some kind of alkenes, and these, upon treatment with ozonolysis, they give you carboxylic acid. And the two carboxylic acids that have been suggested are the benzoic acid and acetic acid. And the question is that the proton NMR of B and C, that is very similar. Treatment of both B and C gives you benzoic acid and acetic acid. Figure out what these structures are. So realize that since this is an alide, it must be reacting with some kind of a carbonyl compound, and hopefully our formula, if there is a formula, yeah, it says that B and C. Okay, so the formula for B and C is provided. That formula is C9H10. And so that means, let's just work that out. You have 9 minus 10 divided by 2 plus 1. That means you have 9 minus 5, 4 plus 1, which is 5 for the index of unsaturation. So we'll keep that in mind. Realize that in the end I'm getting benzoic acid. That means that a benzene ring is present, and that will take into account essentially 4 of the indices of unsaturation, and the fact that this is these are isomeric and can be subjected to ozonolysis. That should tell you that the last unsaturation is probably coming from a double bond. And so B and C, these should be some kind of alkenes, which is also evident from the fact that you're doing a Wittig reaction. You're doing a Wittig reaction. So you have to start with a carbonyl that is going through a Wittig reaction to give you B and C, and then upon oxidation, those are going to break down and give you carboxylic acid and acetic acid. So like I said, benzene ring that is present in these structures. And if I'm getting essentially, so let's work out the ozonolysis product first. This can be one structure. This can be another structure. And the reason why I say that is because if I cleave that off with ozonolysis, or maybe KMNO4, if I cleave that off, then that would mean that I will get oxidation product here. First, it will get converted to the aldehyde, and then since aldehyde is susceptible to even aerial oxidation, is going to give you benzoic acid. And whether it's trans or cis, that reaction is going to occur. So the clue that I got was basically looking at the carbon here and the carbon here, and I just kind of clicked them back. And if this is my alkene that I'm supposed to be getting, realize that I have the CH3 and the C from the ellide, and that leaves behind essentially a carbonyl compound. That carbonyl compound will have to be benzaldehyde. So the way the reaction will work is benzaldehyde is going to react with the ellide CH3CH with a negative charge, and the PPH3 with a positive charge, and the negative is going to attack the electrophilic carbon, and the oxygen is going to attack the phosphorus. It's going to give you the betaine. So the betaine will look something like that, PPH3, like that. And now the PO bond and this to give you cis and trans alkenes as your final products. Okay, the last question included this kind of a schematic, and you're supposed to provide the reagent conditions. So realize the very first one is essentially this ketone getting converted into a secondary alcohol. That means you need some kind of a reducing agent. So you can choose to use something like sodium borohydride in THF. You can also use lithium aluminum hydride, THF. Either of the two will work just fine, and that will give you the secondary alcohol. The next step is the generation of the epoxide. Realize everything else is the same, but you're able to generate an epoxide in this part. That means if somehow you're able to remove this proton and then that negative charge attacks in an SN2 manner and bromine leaves, that will do it. So recall that treatment with sodium hydride, sodium hydroxide, that's going to pull that proton off, generate the negative charge. So let's show that, and that will attack, bromine will leave, and you will generate your epoxide. I would use just sodium, just aqueous sodium hydroxide, and that'll work just fine. And now we are going to ring openness. Realize that still everything else is the same. Let's maybe number this 1 and 2. 1 and 2. So you want to ring open it from the side which is closer to 1. That means you have added this part as your incoming nucleophile. Realize just like ammonia, organic amines are basic in nature, and so that makes sense that if you have something basic, isopropyl amine in this case, will be your nucleophile that's going to attack position 1, that will ring open, so isopropyl amine followed by hydrolysis, so that you don't have a negative charge but actually an alcohol. And past that, let's see, what have we done? Yeah, so past that you have OCH3, so you're going to get rid of that CH3, and the best way to do that is treat it with an acid. So something like HI and then heat it, that will get rid of the CH3, and you're going to end up with the corresponding alcohols. Hopefully this made sense to you, and if you have any questions, feel free to talk to me tomorrow. All right, good luck.